Hi, I'm Bjorn Therese with a follow-up to part 4 of the Controlled Concepts videos. In the previous video, we encountered self-oscillation in the feedback loop when the gain was too high. The gain that causes an onset of a self-oscillation is called the ultimate gain, and the length of one period during this oscillation is called the ultimate period. They are both important dynamic characteristics of a loop and are used in a number of loop tuning methods. In this video, we'll explore how the ultimate gain and the ultimate period correlate with the other process parameters we have worked with so far, namely the steady state gain, the time constant, and the dead time. In part 2 of the series, we looked at step tests from 4 different cases, each with a unique dead time to time constant ratio. In this video, we'll repeat the step tests of the same 4 cases, but now under proportional only feedback control. Therefore, each step is from a set point change between 50 and 60 degrees on the tank temperature controller. I will turn off the audio during this test to give me the opportunity to speed up some of the segments in post-processing. Each test consists of the following steps that you will see in the video. Switch the controller into manual and set the output to 34.5%. That's to get the steady state of 50 degrees in the tank. Set the desired dead time and tank level pertaining to the particular case. Set the controller gain. Switch the controller from manual to automatic, and then set the set point to 60 degrees and observe the response. Notice that I had determined the ultimate gain prior to the test to speed up the experimentation. So let's get started. Hi, I'm back with a table of the test results. I previously determined the ultimate gains to conserve time. I read off the frequency from the strip charts, and you can easily verify these values by going back in the video to each case. The ultimate gain and period vary quite a bit in these experiments, and at first glance it's hard to see what they depend on. However, remember that the ultimate gain and period are not independent variables, but they depend on the dead time and time constant for the process, where those two parameters characterize its dynamics. Therefore, it's fairly straightforward to use mathematics to find useful relations between the various entities. These two charts provide such useful insights. The top chart says that if we know the dead time to time constant ratio and the steady state gain, we can quickly determine the ultimate gain. The bottom chart says that when given the dead time to time constant ratio and the dead time itself, we have the ultimate period. Notice that the ultimate period to dead time ratio is confined to a value between 2 and 4. Doing experimentation with the P-only controller for disturbance attenuation, we noticed that we got better performance with a higher controller gain up, of course, to the ultimate gain. Therefore, if our objective is to have as high controller gain as possible, a process with a small dead time to time constant ratio will be easier to control than one where the ratio is large and dominated by dead time.